Sorry. Okay, perfect. Hello, everyone. Thank you very much for being here and also for the commission to attending to my defense. I am Eduardo Droguett, and today I will defend my work called Spatiotemporal Complexity in Dissipative Structures. Perfect. So, dissipative structures are studied in the context of out-of-equilibrium systems. And you may wonder, what is an out-of-equilibrium system? And I should tell you that almost every system that we see every day are an out-of-equilibrium system because we live in a constant energy injection and also energy dissipation. So, and these far from equilibrium or out of equilibrium systems are defined as systems that have this characteristic, and also they exhibit some nonlinear phenomena that emerges, especially in the systems that are under a high injection of energy and a high dissipation. And these nonlinear phenomena, they correspond to situations where responses are not proportional to the perturbations that are producing them. Okay. Now, going into the dissipative structures emerge in these systems via irreversible processes that organize these several systems into several states that present some order through a spontaneous breaking of symmetry. And these are robust phenomena because they can be observed in several natural systems, such as we can see in these pictures. So one of the dissipative structures that I will be studying in my work are patterns that are in this size. Patterns correspond to an extended dissipative structure that is characterized by their periodicity. We can find them in liquid crystal light bulbs, in optics. We can find them in vegetation also, surprisingly, chemical reactions, and also in the fur of some animals. So this is one of the dissipative structures that I have studied, and the other one are localized states that are a particle-like solution, a particle-like structure that is characterized by being by having a well-defined position, by having well-defined interactions, etc. And we also can find them in several natural systems, such as granular matter, vegetation also, optics, liquid crystals, and colloidal liquids. So these are the two main dissipative structures that I have been studying. And due to their universality, they can be described by universal equations. One of them being the Turing-Swift-Hohenberg equation. The Turing-Swift-Hohenberg equation is, as I said before, an universal equation that allows us the study of these dissipative structures. This is the equation, well, is presented here, where the variable u is a simple scalar that can account for many physical quantities depending on the physical problem that we are studying. For instance, it can account for molecular orientation, and if we are studying liquid crystals, it can account for biomass in the case that we are studying vegetation patterns, luminic intensity, radial displacement for elasticity problems, etc. And the parameters that this equation have also depends on the physical problem that we are studying, but in particular, mu is the bifurcation parameter, and nu is the diffusion or anti-diffusion constant, depending on the sign of mu. So this equation, Turing-Swift-Hohenberg equation, describes a variational system, which means that the dynamics that we observe for systems that are well described by these equations corresponds to the minimization of a Lyapunov functional, that is the one that we are seeing in this big calligraphic F. So what we see is that when we start the evolution of a system that is being described by Turing-Swift-Hohenberg equation, the system will have some relaxation towards a system that minimizes this Lyapunov functional. And then we will have some stationary state. But this is not the case for every system. We also see every day that things are moving, and this is because we also have some systems that are non-variational, which means that they cannot be described by the minimization of this lie upon not functional, because maybe we can add some non-variational terms to this equation. And what we see is that now they exhibit permanent and complex temporal movement, temporal motion, temporal dynamics, and also they exhibit some complex spatial distributions. So we can see here the comparison when the system is variational. This is a video, but as you can see, it reaches towards a stationary state. But when the system is non-variational, we can see that the system exhibits temporal dynamics and also some complex spatial distributions, as I said. Now, this opens some key research questions. Of course, the big question that my dissertation wants to answer is, what are the universal features that define this spatiotemporal complexity that we observe in dissipative structures, and what are the underlying instability mechanisms that lead to this complexity? And in this context, my thesis wants to more specifically answer these 4 questions that are below. First of all, how can the spatial complexity of banded vegetation patterns can be characterized and understood? Then, what is the route to spatiotemporal complexity in systems that form pattern or in two-dimensional system in general? Then, what is the dynamics of localized states that are being forced spatiotemporally? And finally, some new topic also, but also framed in these dissipative structures, is how can extended systems, how they behave under a delayed feedback. And to answer these questions, my thesis have 4 parts. The first part is regarding the spatial complexity of vegetation patterns. Here we have a already published paper, we have a submit paper, and also we have another work that is currently being written. Then, regarding the transition to complexity in pattern-forming systems, we have a published paper in Physical Review Research and also a proceeding for SPIE. And also we have some other work that is currently undergoing. Then the third part for localized states under a spatiotemporal forcing. This is a very interesting subject. It's also a work that it's currently submitted for peer review. And finally, for delayed feedback in extended system, this is also a really new topic. One of them is going to be presented later this year in a conference in SPIE also, and the other ones are being worked also. So this is a lot, of course, but this presentation will only focus in the first part, in the spatial complexity in banded vegetation patterns. If you ask me why, because I think this is a great motivation, in fact, was my motivation for studying nonlinear physics. And also, I think it encompasses very well all the techniques that we use in nonlinear physics and all the techniques that I have been using during my master. So, going into the spatial complexity in banded vegetation patterns emerge due to the scarcity of resources in semi and arid ecosystems, in arid and semi-arid ecosystems. And this phenomenon can be observed in several or various types of soil, in several or various species and scales of the system, and also it can be observed widely across around the world. Now, this deformation of deformation of vegetation patterns can be understood or can be explained by the interplay between some characteristic lengths. One of them being the facilitation, the length of facilitation, and the facilitation is produced due to the sheltering that a certain species, a certain plant effects into their neighboring plants. And also this competes with the, well, this feedback, this positive feedback caused by facilitation is also going against the competition that generates, for instance, in this case, the roots of a system, but in more general, is the competition for resources that are scarce in the systems that we are studying. And for patterns to form, the competition interactions must be of a longer range than facilitation. Now, going into a more specific topic, because I studied mostly banded vegetation patterns. Banded vegetation patterns emerge in anisotropic systems, where due to a certain environmental conditions, such as wind, such as topography, such as other conditions that may affect and add a certain characteristic direction, patterns reorganize into a banded manner, as you can see here. So they exhibit a certain well-defined direction, and also they exhibit propagation in the direction they propagate towards where the nutrients come from. So as you can see here, due to the propagation of wind or a fog, we see that at the level of species, they are anisotropic, and this turns into banded vegetation patterns, as you can see here, and they propagate in time, as you can see in this transition map. Now, banded vegetation patterns can be observed, as I said before, in several places around the world. As you can see here, several continents, but they are a little bit different if we want to compare with the theory of pattern formation. Why is that? Because they present some irregularities. In particular, these are like the main irregularities that I could identify. They present irregular interfaces, as you can see here. They are not perfect or smooth. They have some rugosity. They also present some non-uniform boundaries, as you can see here. They have some variable widths. As you can see, these are not always the same size, but there are some thicker and there are some thinner stripes. They also present some local periodicity shifts. As you can see, they are not perfectly periodical. Also, they have some varied orientations, and they present some dislocations. So you can see here where two stripes merge into one. And this also is a break of the periodicity of patterns. So these all are irregularities of the observations of vegetation patterns. And we want to, of course, characterize them and try to explain them, because let's say the theory of pattern formation that it's most generally used don't account for these irregularities. So firstly, I want to address the width of the bands. So this is one of the works that has been published already, where we study the distribution of the stripes that conform the vegetation pattern. So as you can see here, we define a certain width L, and we plot their distribution. And interestingly, what we see is that they don't follow. They don't follow, let's say, one thing that one could expect, a Gaussian distribution, because Gaussian distribution should be expected for maybe stationary processes, but they follow a Gaussian distribution. So this is a heavy-tailed distribution that extends from the Gaussian, of course, but this has been used for non-extensive statistical mechanics in the context of systems with long-range correlations and memory effects. So this is really interesting because it's giving us some insight maybe on these effects, and that the irregularities of patterns are not merely stochastic due to maybe noise or irregularities, but there is something else making that these distributions are different from a simple normal distribution. Now, going a little bit further into the bands, we studied the interface of the band, as you can see here. So what we did is that we extracted one band, like here, and we defined a skeleton. And from the skeleton of the band, that it's like the middle point, if you want to define in that simple way, the band, we defined the interface. That is the distance from the from the outer point of the band to this skeleton. And these interfaces have been of great interest of studying in physics. In particular, one of the things that can be studied or analyzed is the local interface width, this W that you see here, that account for how much it varies the interface in this local, let's say, region L. And why this is interesting of studying, because it has some interesting insight on the rugosity of these bands, because we can compute the roughness exponent that corresponds to the power law increase exponent of the local width of the interface. And this number can quantify the degree of irregularity of a certain interface. So we computed this roughness exponent in every vegetation pattern, banded vegetation pattern that we could find. And what we observed is that the roughness exponent, firstly, is not constant, but varies according to the place in the world that we are studying. It varies between 0.8 and 0.95. So this is very interesting, first of all, because we can find some scaling laws in this system, but also because there is some universal framework for the studying of interfaces, that is the KPC equation, that is this equation that it's up here. But this universal equation that has been studied for propagation of several interfaces, such fires, such also growing interfaces, etc., predicts a roughness exponent that is constant, predicts a roughness exponent that is 0.5. But this exponent is really far from what we observe in vegetation. So this tells us that vegetation patterns, or the interface of vegetation patterns, are not entirely well described by this KPC equation, but we need to take into account another thing, another characteristics of the system. And what we saw is that if we take into account the spatial inhomogeneities that are static, maybe due to topography, maybe due to the irregularity of the floor, but the important thing is that to our universal KPC equation, we add some stochastic variable that is the spatial inhomogeneities. We now observe that the roughness exponent varies. It's not constant like the original KPC equation, but it varies accordingly to what we observe, because we can shift the roughness exponent between 0.5 and 1 according to the intensity of the inhomogeneities, and also according to the correlation length of these inhomogeneities. Why? Because we use some smooth inhomogeneities to account for our real world conditions. And this is really interesting, because we are seeing that the statistical laws that we observe for vegetation patterns, for the interface of vegetation patterns, emerge due to the static inhomogeneities of the system. Well, this is, as I said, a really good insight. It can lead us to new information of the environments that we are studying. And to extend, of course, our studies, we use some theoretical modeling. There are several theoretical models that has been used for studying vegetation patterns. The one that I used the most in my master was this integral differential model that you can see here, that accounts for the non-local interactions and the anisotropies in the environment. So as I explained before, patterns form due to the different length scales of interactions in the system. And this is a model that takes into account that. So this model is for the biomass B of a certain system and corresponds to a modification of a logistic growth. But it has some non-local parameters, this MF and this MC, that account for the different interactions. MF accounts for the facilitation, and the shape of the interaction of facilitation if the system is given by the kernel, this KF accordingly. And this MC is the competition kernel or the competition parameter that is also non-local, and its shape is given, of course, by another kernel. And also we consider, for simplicity, that the encroachment of vegetation and also the propagation of speeds is simply diffusive. Now, if we perform some numerical simulations of this model, we observe, interestingly, that without inhomogeneities, this has been already published, which means without this stochastic smooth term, we observe that the Q-Gaussian distribution also accounts for our numerical observations. But interestingly, if we add the spatial inhomogeneities, we observe that, in fact, indeed, the roughness exponent varies as a function of the inhomogeneity intensity. So for no inhomogeneities, the roughness exponent is 0.5. This corresponds to the universal KPC equation. But as we increase the intensity of these inhomogeneities, it goes towards our observation values that are close to 0.9. So we are pretty confident that these inhomogeneities are what is shaping the irregularities of the vegetation patterns that we observe. So this is regarding the widths and the irregularities of the interface of vegetation patterns. But now I want to highlight some previous work of a previous student of my advisor, Marcel, which are the study of the dislocation distribution. As I mentioned before, one of the irregularities that vegetation pattern presents are these dislocations, where two stripes merge into one. And they studied that in these banded patterns, these dislocations do not distribute evenly, but they distribute according to this logarithmic law that you see here, this logarithm x divided by x. And this is really interesting because this was a universal law that was observed also in several places around the world and also was studied numerically. But there is some problem. And the problem is that on one hand, the study of vegetation patterns can be really useful for understanding what is the health condition of these endangered systems, but they have some really complex and, let's say, difficult spatial and temporal scales. Of course, these extend in kilometers, and their temporal scales, as you saw before, they travel at the order of centimeters per year. So making direct experimentation and also direct measurements that are not satellites, it's really impractical. But the good thing is that, as I told you at the beginning of my presentation, the pattern formation is universal. So we can study or we can use some optical analogs or analogs in general to further understand these systems. So in this next part of my presentation, I will shift towards a more experimental, let's say, approach of this pattern formation using some optical systems and in particular using liquid crystals. Liquid crystals are a state of aggregation of matters that is characterized by having some solid properties and some liquid properties. In particular, it has the fluidity of a liquid, but also has some order like a solid. And this order varies when we change temperature. So for us, for a low temperature, we find a solid phase where liquid crystals have molecules have some positional order, as you can see they're organized in a grid, and also have some orientational order. Every molecule is pointing more or less in the same direction. And if I increase the temperature and I go to the other extreme of my picture, we have the liquid phase, where our molecules are distributed, they're not organized. They have some lost in the order of position, and also they lost the order of orientation. And in the middle, we have the nematic phase, that is the phase that we use, where liquid crystals are, they lost already the positional order, but they keep some orientational order in average according to a certain director N. Of course, this can be defined thanks to the anisotropic properties of the molecule. As you can see here, it is like a grain of rice, the molecules that we use. Of course, this is a representation, but they have some anisotropy, and this director N corresponds to the direction where these molecules are in average pointing to. Now, liquid crystals have some really interesting properties also, according to their elasticity, because due to their anisotropy in their shape, they behave like every medium as an elastic medium. And also, but what I wanted to say is that due to their anisotropy, they exhibit 3 modes of deformation according to the type of deformation that we are seeing. So we have splay, we have twist, and these have bend also due to their anisotropy, as I said. And also they exhibit some interesting electric properties where when we applied a certain electric field, depending on the electric anisotropy of these molecules, the director may reorient towards parallel to the electric field, applied electric field, or orthogonal to the electric field, as you can see here, depending on the dielectric anisotropy. But we see that in general, these liquid crystals exhibit some strong interactions with these applied external fields. And finally, another interesting property that we use for our experiment is that they are birefringent, which means that when we shine a certain polarized light with a certain state of polarization, liquid crystals change their state of polarizations into another, let's say, another state, of course, and there is a phase shift that corresponds to this equation when, of course, the light shines through this liquid crystal media. Now, we use all of these interesting properties of liquid crystals to build and to use and study this liquid crystal light bulb that you can see here. So liquid crystal light bulbs are a liquid crystal cell, which means we have 2 glasses and some liquid crystal media. And also they have some indium tin oxide plates in this cell that allows us to apply some external voltage, V0, that allows us for reorienting the molecules as we want. As I said before, because they react to an external electric field. But also, this liquid crystal light bulb is divided into 2 zones, 2 regions. The lower region that we have here is the reading zone that allows us to shine a certain beam, light beam, with a polarization that we know, and then the light beam passes through the liquid crystal media and get reflected by this Bragg mirror. So this light beam that comes out of the liquid crystal light bulb has passed through the liquid crystal media, and as I told you before, now it has, in the state of polarization, the information on the orientation of the liquid crystal molecules. So it has in the local points, in each point of the transversal plane of a certain beam that was shined through the liquid crystal light bulb, it has the local information of the orientation of liquid crystals. And in the other region, we have the writing region, because we can shine also a light beam, and there is a photoconductor, as you can see here, this PC, and this photoconductor translates the light intensity, the local light intensity, into local voltage. So we have a certain homogeneous constant applied voltage, or well, we have a applied voltage, and also we have an additional voltage that varies locally according to the light intensity of a beam that it's being shined in this region. So this liquid crystal light bulb is placed into this system, this setup, that is the liquid crystal light bulb with optical feedback. So what we use is that we have this helium neon laser that we enlarge using this microscope objective, and shine through this spatial light modulator. This spatial light modulator is also a liquid crystal display, but it is a liquid crystal display that we modify or we control using a computer. And this allows us to modify the transversal intensity profile of the light. So we can, if we want to study some problems that has some maybe square boundary conditions, we can put a mask in this SLM that is a square. We can use a circle, we can put any picture that we want. And also something that is important for the fourth part of my thesis, we can also put videos in this spatial light modulator or change it in real time. But the important thing is that the laser shines through this spatial light modulator and now passes with the spatial intensity profile that we want. And then it goes through the liquid crystal light bulb to the reading zone. Sorry. And then it gets reflected with its polarization state being our way to know how the liquid crystals are oriented. But then it goes through this polarizing beam splitter that translates this information that it's encoded in the polarization, it translates it into intensity, light intensity. And one of the parts, or one of, let's say, a fraction of this light intensity goes towards our CMOS, our camera, where we observe what is happening in the liquid crystal light bulb via the translation of the polarization state to intensity. But the other fraction of the light intensity goes to the right-hand side of the liquid crystal light bulb. So we have a feedback loop where the information or the state of the system that comes out for the liquid crystal light bulb goes again and retroject into the right-hand side via this photoconductor. So this system is interacting with itself quasi-instantaneously, of course, because liquid crystals have some slow time of reorientation compared to the time that takes for the light to travel between the reading zone of the liquid crystal light bulb and the writing zone. So this feedback is instantaneous. And here it is a picture of our nice experimental setup. I want to say that the laser is not that powerful, of course. This is just a representation of the laser, is painted. But this is an experiment that we use for studying. And what can we study in this experiment? Well, we can study, for instance, these banded patterns in a more controllable manner. So this is the same experiment that I showed you before, but it has some modifications of some parameters that we can move. In particular, in this case, we can move the fiber bundle that controls the retroinjection. Why? Because in the way that the system was presented in the previous slides, the retroinjection is practically self-imaging. Of course, we have some error. We cannot find the 0 point exactly, but it's practically self-imaging, where the image that comes out from the liquid crystal light bulb is the same image that goes to the photoconductor. But this only yields homogeneous states. This doesn't yield some patterns that we want to study. And in order to have patterns, we can add some free space diffraction in the system that is made simply by displacing the entrance of the fiber bundle. So if I displace this parameter L that you see here, and I displace it closer to the liquid crystal light bulb, we have what is called a negative diffraction, and this is what allows for the pattern formation as you see here. This is the patterns that are formed when I only displace the fiber bundle in order to have negative diffraction. But the pattern is anisotropic. Sorry, it's isotropic. The pattern is isotropic because it doesn't have a characteristic orientation, as you can see here. And we want to study banded patterns. And to have that, and to have also propagation, what we do is that firstly, we displace also the fiber bundle, but vertically or horizontally as we wish. In this case, I displace it vertically. And this allows us to have non-reciprocal interactions between the molecules. Why? Because now, when the retroinjection is displaced, the image that comes out from the liquid crystal light bulb gets retroinjected a little bit upper or a little bit to the down part of the writing side. And this induces some non-reciprocal interactions between the liquid crystal molecules. And this is something that helps us to have propagation and also induce a characteristic direction. But in order to fully have our banded patterns, what we can also do is that we have here a mechanical slit in what is called the far field of the system. And this helps us to eliminate some Fourier modes of our system. And then we can have, or we can shift this isotropic pattern to an anisotropic pattern that is what we want to study, these banded patterns. And what do we observe? We observe that we have two operating regimes by changing the fiber bundle vertical displacement that I told you before that corresponds to the non-reciprocal interactions of molecules. And these two regimes exhibit some different distribution of dislocation and also some interesting different dynamical features. And when we study the distribution of dislocations, as I explained before, we observe that for a small translation of the optical feedback, we see this interesting logarithmic law that was previously reported for vegetation. So this, again, reinforces the universality of pattern formation and the usefulness of these optical analogs to study pattern formation and pattern systems. And as you can see here, disregarding these boundary effects, we have this nice law that was observed in vegetation. But if I further increase the vertical displacement, we observe another region that it's more or less where it has some more or less even creation and even distribution or constant distribution of these dislocations. Interestingly, this distribution was not observed in vegetation. So as you can see here, these optical analogs allows us to extend the studies that was performed in vegetation into a more fundamental approach. So we have these two different regimes of dislocation distribution, and now we want to understand why do they emerge. And to do that, another good thing of these experimental systems is that when we work with vegetation, we can only use theoretical modeling, but it's not based on first principles, of course. We don't have some first principles equations for vegetation. But in the case of these controlled experiments, we do have some insights on the first principle equations that govern these systems. And also because this model also was obtained using some precise fitting of the experiment. So we can control more, and we can have some more models that we are sure that correctly describes the physics of the system. And this is the case of this model. This model is for the angle of reorientation of our director N. And it's a relaxation equation where the angle of equilibria depends on our parameters that are the voltage that is being applied, the light intensity, the displacement of the fiber bundle, the diffraction, and of course, this term corresponds to the light matter interactions when the light passes through the liquid crystal cell. So we have this model, and we can study some interesting numerical simulations, and we observe the two regimes that we observed before in the experiment, and we observe also the logarithmic law. But this is a really complex model also. It's non-local. It has some really complex terms, so we can perform some local approximations and placing us in the point of nascent stability and spatial instability, and perturbing this state, we find a Turing-Swift-Cohen equation, but with some terms that account for the more specific properties of the system. And of course, each parameter corresponds to a certain amount, a certain function of the physical parameters of the system. And we observe also these patterns. But we wanted to go a little bit further into this. We want to study the dislocations, and the dislocations are topological defects if we study the amplitude of the pattern. So we derived the amplitude equation of our patterns that are being studied. And to do this, we took into account the boundary layer that is being formed in our system. We took into account the homogeneous base solution, and we wanted to find an equation for our pattern amplitude. And when we insert these ansatz into our equation, our local equation, we find some universal model that is the homogeneous Gisborne-Landau equation with advection. Well, the Gisborne-Landau equation is a universal model that has been used for studying several systems that exhibit topological defects. But here we have some inhomogeneous terms that correspond or that are there because of the boundary layer in the system. And also we have some nonlinear dispersal that arises due to the displacement of the fiber bundle. And what we observe is that when we change this nonlinear dispersal for a low nonlinear dispersal that corresponds to a small displacement of the small vertical displacement of the fiber bundle, we have that the dislocations distribute according to this logarithmic law. So dislocations here correspond to the topological defects that are these points where the phase is not defined and the amplitude goes to 0. But if I increase the nonlinear dispersal, we reach to a state where dislocations or these topological defects are created everywhere. And this is what leads us to the constant distribution of the dislocations in vegetation and in our experiment. So, as we see here, this amplitude equation revealed that for our distribution to arise, there is a balance between the non-reciprocal coupling induced drift, because they are traveling downwards. There is also a balance with the boundary layer instability that creates the dislocations. And also there is an interesting or an important effect due to the interactions between topological defects, in particular that they repel or annihilate or according to their topological charge. So in conclusions, I will divide the conclusions in two sections. The first one is only for this presentation. In conclusion, for this presentation, vegetation patterns are not regular. They exhibit several irregularities that follow some well-defined statistical laws. And optical experiments helps us to, and they serve as an invaluable tool to extend the studies that we perform on this vegetation or in this system that are not very well controlled into a more controllable system and more well understood, that is the experiment. And the distribution of these locations is caused due to the balance between the drift that is caused because of the non-reciprocity, the dynamics of repulsion and annihilation, and also the boundary layer instabilities. Now, more in general, the conclusions and perspectives of my entire work is that we could understand and characterize the universal features of the spatiotemporal complexity in these dissipative structures. And there are some perspectives regarding to the direct ecological link of our universal results to what is happening in vegetation systems. Also, regarding the second part of my thesis, that is the formation or the route to spatiotemporal complexity, there is some future work, numerical and theoretical work, that has to be done for quantifying some of the transitions. In the case of the localized states, there is an experimental demonstration that is lacking still. Of course, we have some interesting theoretical results, but this always needs to be well-founded by experiments, so this needs to be done. And finally, in the topic of delayed feedback, an entire landscape of research has emerged This is really nice because now we can study these interesting systems where delayed feedback is taken into account. So a big shout out to, of course, our group. Of course, science is not made alone. It's made with all the group and all of the people that I've worked in these years. And thank you very much for the kind attention.
Thank you, Eduardo, for the presentation. So now we're going to proceed with the questions from the members of the committee. And from the list, first I have Dr. Adrian Dyer. So if you will, please.
Okay, thank you. Thank you for. I'm maybe also the one maybe least familiar with my first. I'm very honored that you invited me to your jury. It's my first jury in for Chilean master. So if I don't know if I kind of interrupt me if I what I say or so is not in the usual format, is going way beyond what is supposed to be, or something else. Yeah, thank you. So I really enjoyed the reading the manuscript also, which I find remarkably clear. So because really right from the introduction, there's a very apparent effort to structure the subject and so there's a lot of chapters in your work, and they kind of quite naturally follow one another, and so you really manage to motivate what guides you from one to the next. And so I'm quite certain that the students who Eduardo teaches must appreciate that kind of clarity. So another uncommon feature of this dissertation is that it's goes without hesitation back and forth between theoretical considerations, numerical simulations, observations, experiments, and treating all with the same attention. And that is kind of rare, but that's how physics should be done. I particularly appreciate this kind of step to both looking at observation data like the vegetation bands, and also using well-controlled laboratory system like this liquid crystal light valve for which the first principle physics is known well enough, and Eduardo and collaborators managed very elegantly to derive pattern formation models, Turing Swift-Hohenberg equation. And so that is really a nice that was a nice read. And then I'm very excited indeed to see what this time delayed feedback in the system opens for new possibilities. Just a last element in the manuscript I found quite remarkable was the perspective sections that follow each chapter, and that show both a solid knowledge of the state of the art, a capacity to put results into perspective. And so I find the kind of the sense for relevant questions of around the subject is really remarkable for this early stage in the career. So a few questions, if I may. Yes, one. Let's start with interface roughness of these banded structures. Could you elaborate? You introduced you say it needs spatial inhomogeneity to appear, but in your equations there's also, at least in your manuscript, it was not on your presentation, there was also a time, there was noise in time. Could you elaborate on the importance of that? Is that and what is the effect of that additional noise?
Yeah, of course. First of all, the KPC equation, in order to have this roughness exponent close to 0.5, needs to have this spatiotemporal noise.
Exactly.
Interestingly, the intensity, it can be understood via scaling, but the intensity of this noise do not affect the roughness exponent. Of course, in our simulations, in every simulation that we perform, we had these spatiotemporal fluctuations because real-world systems have some fluctuations. And also, when we add the spatial inhomogeneity, I did not mention it because it has the same effect of KPC the equation. If I change the intensity, it doesn't change anything else. It's just the intensity of the inhomogeneity that is what is changing the roughness of the system.
Okay, thank you. Interesting. Speaking of KPZ, though, this is for a growing interface. When you showed your experimental or your observational data, and you showed how you walk around one strip and measure the front shape. Well, you consider both the front and the back of a strip, but it's a propagating structure, so you could argue there's one growing front and one receding front. Would you? Well. Could you still argue how you can describe that with the same equations? Do you need two equations? Can they interact or?
Yeah, no, that is true. In fact, if we observe the numerical simulations, we see that the front end of the stripes is different to the back end of the stripes. So yeah, that is true. That is something that it's yet to be understood. But what I can tell you is that the crossover of our roughness of our intensity with, interface with the crossover is at the order of, let's say, less than a stripe, less than a, let's see, how can I explain? The crossover is like 1/4 of the full perimeter of a stripe. So maybe it is changing that we are taking into account all of the stripe, but the interesting properties or scaling properties of the system are at the order of 1/4 of perimeter and not the full perimeter that one could maybe say that it's changing something. So yeah, that is something that needs to be studied yet, but I am really sure that the crossover is not at that order, so that is something that quite, well, comforts me a little bit. Of course,
Okay, so sorry, just to make sure, by crossover, you mean that you see this scaling for the short length scales, and it kind of fails then at the longer length scales. Is that what you mean in the bottom right graphs?
I mean this length right here, this L, is at the order of this quarter stripe, not 1/2 or not the full stripe. Yeah. So it's not going all of the round. That's a nice question.
So there was another question, but I think I don't know, you didn't show these data, but I may nevertheless still on the vegetation bands, but you look at the power spectra, and you underline an exponential decay of the biomass spectral density. So at large K. Exactly this kind of exactly. So it was in your presentation, right? So no, you didn't show this one. So my question is it's a bit provocative question, but because you describe how you process your data and so on, and you say you smooth it a bit with the Gaussian filter. That's a low pass filter, and so basically, if you filter it with a low pass, you expect the power density to go down exponentially at some. So is this may this be a consequence, or there's a kind of correlation between the ones where the decrease is strongest are also the ones where the spatial length scale is shortest. Is there a link between that, and could it be kind of not if not entirely an artifact, but affected by the processing itself, by you or by Google or by even the satellite acquisition?
Yeah, of course, that is actually a really good question. In fact, it is one of the questions that we got in the peer reviewing process of this project, this work, because previously we were working with binarized models, with a binarized images, and this yielded some power law decay with -2. And that was an artifact because then we changed to the grayscale of the images. And well, I've tried with some different Gaussian filters and I have not seen that it changes. I am pretty confident that this is more regarding to the properties of the system. But of course, I agree with you that every time we filter something, we are making some changes. The thing is, if they are small or they are big in the results that we are seeing. In my case, I try to with several different intensities of the filter and without. And well, I prefer to filter some with the Gaussian filter just because at the level of the pixel, it also can be a little bit noisy and also has some structures that we don't want to take into account. The filtering is more to only have the pattern, the pattern structure, and I believe that it does not generate this artifact in the exponential, but of course I can take another look.
Okay. No, it was just it's interesting comments. No, I was simplifying a bit. Of course, if you use the same filter everywhere, and if it was a cutoff effect, you'd probably have the same slope, and which is not the same slope. So something is there's more to it than that, no doubt.
Yeah, makes sense.
I had sorry, there's some bell ringing close by. I hope. I had a small yeah. It's a question regarding the fragility to kind of symmetry breaking.
Uh-huh.
You because as in your introduction also you really nicely explain how bifurcations are fragile, how pitchfork bifurcation with noise easily gets cut
Yeah.
into a saddle node and a stable state. In reality, of course, you always have symmetry breaking effects.
Uh-huh.
So it's almost astonishing why are not all bands vegetative covering banded? You have an
Uh-huh.
idea what degree
Yeah.
of symmetry breaking you require to have this?
Yeah, I would say that it depends on the competitions of length scales. Maybe at the local level, there is some slopes that may shift towards a band, but it's always a competition between the pattern length scale and the length scale of the different symmetry breaking um, effects that has the environment. So that is why we don't have always um, banded patterns. In fact, we observe these nice spots or we observe these nice labyrinthic patterns. It's just a matter of scaling both in the dynamical features, I mean the intensity and everything of that, and also the scaling of length.
Okay. Yeah, convincing. Okay, I don't know. I'm taking much time. Maybe just a small last question, if I may, on the role of the Fourier filtering that you perform in your liquid crystal light
Yeah,
valve system. That's a very nice trick and very convenient, I guess, to kind of favor these horizontal bands to favor one direction by having a slit.
yeah.
But what is exactly how intrusive is it? How is it? How does it influence, for example, the creation of new defects or the creation rates, or does it have an effect on the boundary layer size, or what can you say about this slit?
Yeah, that is actually really interesting because, well, it has not been studied yet. Because, firstly, for me, I haven't think of a way of translating this L that corresponds to the opening of the mechanical slit into a parameter that corresponds to our. Well, here we filter this, but it's in pixels. So for now, I haven't think of a way of translating this into theoretical modeling to studying further. But in the dynamical aspect, yes, there is a huge influence in this filtering, and because we are eliminating modes, and this also decrease the dynamics. In fact, what I have observed for other problems is that if I have this close to zero, I mean really close, the mechanical slit, For instance, patterns are static. They do not move. They don't have dynamic. They're well spatially distributed. So there is a balance. We need to have a balance between some characteristic orientation, but not eliminating the dynamics. And in this case, specifically, if I close it further, we do not have these locations. We don't have them because well, we are eliminating the modes and we cannot have those variations. So I needed to have a balance. Of course, I believe it's a robust balance. I've tried with some different parameters and I have some similar laws. I just presented the ones that I found more appealing, but it is a robust balance, but it is there, the effect. Thank you.
Okay. Oh, thank you. Thank you very much. Congratulations for this
Thank you.
I think, very thorough piece of work, which frankly could be a PhD thesis in France. Thank you also for coming to Paris. I hope you'll have an enriching period, and I'm looking forward to working with you.
Yeah, me too. Thank you.
Thank you very much, Adrian. Now, the next one in the line is Dr. Cristina Soler. So, Cristina, for yours.
Hi, Eduardo. I will pick it up from the previous member of the committee, and I will say that yes, this has the level of a PhD thesis, to be honest with you. So I'm highly impressed by all your results and all your work, and it's particularly for me, it's very impressive that you have been able to do experiments and simulations and models. So that's really very impressive for at any level, but especially for a master student. As you know, I was in your previous defense, so I already asked my main questions then. I am just going to be very brief too, but I have to do my job, so I need to ask you a couple of questions. And the question that I have in mind is actually quite simple, because at the end of the day, I would like to know which for you was the most challenging, the largest challenge in the experiments. So from the experiments point of view, when would you say that it was something that really you struggled to solve?
Yeah, it has to do with what Adrian asked me. Tuning every parameter here to have what I what I was expecting to prove, because I like this kind of experimental approach where we have some insight of what we think is a universal law, and we want to see and show experimentally that law, but that can be really frustrating because you are focused on finding this. And of course, maybe you are missing some other interesting things, but that focus, it's also had led me to be several hours in the experiment because I did not count every control parameter, but we have the diffraction length, one, we have the vertical displacement, two, we have the mechanical slit that affected also, three, we have the intensity of the light intensity, four, we have the voltage, five, and also we have the some other, let's say, calibrations that needs to be done every time that we use the experiment. So that was, I would say, the most challenging thing for me was tuning everything and then doing it again every day and finding some, as I said, some robust regions where we observed this. That was what took me the most hours and the most psychological stress, that I would say. But of course, it's always very rewarding to find them eventually.
Of course, no doubts about it. No doubts about it. Now, my second question concerns something that I think you didn't actually do, which is machine learning, right? So, how do you think if somebody is going to continue your work? Would you find it easier now that after you have done this study and with robust machine learning to identify these conditions or to improve the analysis, the setup?
Yeah. Yeah, well, I will speak something that I've heard a lot that my advisor want to do. And I think it's really interesting because in vegetation, I mentioned that there are a lot of models that exhibit some of the features that we observe. But this, as I said, a lot of models, we need to have one that we think it's the correct one and is correctly describing what we are observing. So I think, well, we think with Marcel that this could be a really interesting machine learning topic that we use that in order to compare these models, compare if we can find which model is the one that is better describing vegetation. And also experimentally, this can be used also for fitting of parameters, etc. But I think vegetation is the place where we need to push this machine learning because also the difficulty of making measures, the difficulty of the scales, etc. I think all of these tools should be focused in the vegetation aspect.
Okay, my third question would be, I know you used this clustering algorithm,
Yeah.
Cummins, in our, so you think it could be useful for the vegetation data? Or have you tried to do it? Did you already try it?
Yeah, I haven't tried, but yeah, of course, I would think it's useful. I mean, it's a tool. One needs to use the tool in a correct way. So, of course, I think that tool can be used and could be useful for maybe differencing the different dynamical, well, not dynamical, but profiles that we see, the different patterns that we observe. Of course, we could start by that using firstly this clustering and then moving to the
Yeah, because clustering is not machine learning, it's just
yeah.
classification, right?
Uh-huh.
It could be a very simple way to try to see if you could classify these patterns in different categories. And
Yeah, of course.
yeah, it would seem to me like a natural continuation or connection with what you have done with the optical patterns, no?
Yeah, of course. That should be the first step before going into the machine
Yeah.
learning, of course.
Okay. And last question, and I finish. Of course, you leave many things open as interesting things to do. And my question is, what is your opinion? Which is if you were going to start a PhD on this topic, which you're not, but suppose,
Yeah.
which of all these very interesting problems will you face first?
Yeah, thank you very much for that question because I can talk about something that I did not talk in this presentation. Because, yeah, of course, it is a good thing to leave problems open. I think that good science leave open problems, but also it is a little bit frustrating to leave a lot of things because it is motivating to keep investigating. What I would do if I would keep here, it's the delayed feedback. The delayed feedback, it's something very new. It's something that has been done theoretically a lot, but experimentally very little, because it's really hard to have, firstly, a control delay, and secondly, an extended control delay. So I would definitely shift into this. We have some interesting observations. We have some spirals. First of all, we have oscillations. Oscillations in liquid crystal media do not appear because they are dissipative. So this is something really interesting. First of all, because we open everything that is related to oscillations to study with our system. And we also can study some things like pattern formation now induced by delay. We can also study front propagation with delay. So I would say that, of course, everything everything gives some perspective for future work, but I would think that this is I would say that this is like my I don't want to sound like it's my greater
Something that you would love to do.
inheritance.
You
It's my
would really
greater
like to
inheritance.
do.
Yeah,
Okay.
I didn't want to say like I don't know, but it's like my great inheritance is this delayed, I
Yeah.
would say.
Okay, I do have more questions, but for the sake of time, I will let the other two members of the committee.
Thank you.
Thank you very much for your presentation. It has been very, very enjoyable.
Thank you.
Thank you, Cristina. So the next one is Dr. Mustafa Tlidi. Mustafa, all yours.
Thank you very much, Alejandro. And thank you also for this, I would say, outstanding work that we already discussed this. We asked many questions during the private defense. So you clearly show that that you have some level of understanding, which is at the level of the master, is I'm very impressed. I just and also the presentation was extremely good. I mean, well prepared. And this is I would like to congratulate you not only on the part which we work together on vegetation, which your contribution was very important in the field. Especially in relation with this complexity in the vegetal pattern, which is not trivial. It involves the topological defects and the complex, let's say, spatial complex dynamics. You also use many tools to classify, to understand the complexity. Even not only during remote sensing analysis, image analysis, real image analysis, but also you work on the lab, which makes this this fantastic logarithmic x over x. It was shown by analyzing remote sensing analysis, but the vegetation part of the measure are not so precise comparing to optics. Optics is fantastic because we can measure things with some level of fiability. I mean, this rather, I mean, so your contribution in this part is mainly to show that this law it exists not only in vegetation but also in optics, which is very impressive, like a conclusion, because optics and vegetation somehow are very different. Yes.
Yeah.
So now, regarding just spatial complexity, let's say you have a structure which is spatially complex. You do Fourier, so Fourier it is an excellent tool to classify those patterns, but Fourier is limited.
Yeah.
Now, you use also this entropy to measure the complexity in your last paper. So my question is, because the title of your master thesis looks like a title of a book.
Yeah.
Complexity in dissipative structure. It looks like
Yeah.
like a book. So you explain what is dissipative structures in the beginning,
Yeah.
but in your opinion, I already asked this question, the private defense, I just repeat this question. What is the tool, for instance, when we deal with spatio-temporal chaos, there is complexity, you know how to characterize this. It's Lyapunov spectrum. Yes? This is the main characteristics. But now, if you have a pattern that doesn't evolve in time, it is stationary in time, but complex in space, what is so you use many tools. What is the tool that really can characterize? So Lyapunov spectrum, forgot about, because this is really complexity in time, but in space, what is?
Yeah. That is well a good question, of course, as I told you in the private. Um, and I would say in the same manner that I said the other day, that we cannot focus on only one tool. Yeah. For instance, if you want to build a house, you cannot do that using only a hammer. You need to have different tools for different things that you want to do. And I would say that for building this house, that is understanding the spatial-temporal complexity in these patterns, we need to complement tools using, for instance, as you said, the Fourier one. The Fourier one helps us to understand the periodicity aspect of the patterns, but we cannot understand at the level of the interface what is happening. So we need to also understand some scaling properties. That is also a nice tool, scaling properties of the interface, and going into a more dynamical regime. Of course, in vegetation is hard, but statistical mechanics and statistical tools also helps us and can be used using analogs to understand dynamical aspects of the system. So I will not marry with only one tool, but I would say that we need to understand what is each tool giving us information, and in order to have the full insight of the system.
Okay. So thank you very much again, and I wish you a brilliant future. You are moving to Europe, and Paris to Paris. Paris is not far from Brussels, so you are always.
All will be close. Yeah.
Thank you very much. Yeah.
Thank you.
Thank you, Mustafa. So the next one in the line is Dr. Mario Wilson. Mario, all yours.
Hello, thank you so much. Eduardo, congratulations. I agree with all the committee members. You did a brilliant work, and I'm very happy to hear you and to see you, even though I'm not at Santiago right now. But well, I believe we will meet in San Diego, so it will be soon. And well, unfortunately for me, my colleagues did all the questions, or almost all the questions I can have in my mind right now. But I have some. It's more like a curiosity thing. But I was thinking before in this link that you present between the vegetation patterns and the optical one, and I'm always wondering about the time frame. We do know that vegetation time frame is really long compared to the optical one.
Yeah.
And I was wondering if you have some way to verify if the rowing mechanism or the mechanism behind the thing that leads this rowing coincides with the optical one. I mean, maybe it's not just something that you can argue about, but it's a curiosity thing. Have you think about it?
Yeah, actually, that is really interesting. I haven't given a thought of that, but what we can do is that we have measured the velocity of propagation of the patterns, vegetation patterns,
Okay.
By using several satellite images in several times that we have, of course. Well, that is something hard because we are fighting with the resolution of older satellites, etc. But we have some estimate, and of course we can adimensionalize those times, those spatial scales, and compare it with the adimensionalized experimental ones. So yeah, that will be also an interesting thing to look at. And also because, as I previously mentioned, there is no observation yet on the constant distribution of these locations. And this constant distribution arises when, experimentally, when we have a higher non-reciprocity and patterns travel faster. So that if we can find this constant distribution in vegetation, we can then use your idea of comparing the timescales of propagation. So yeah, that could be done, and it would be interesting if we can find this law in vegetation.
Yeah, sure. Because I believe that due to different characteristics around the world, you will have like different growing ratio. So
Yeah.
maybe you can, well, I don't know if you will do it, but someone can like trying to find a way or a place where the windy conditions are really strong, for example, and you can lead a little bit to that regime. Well, I'm just wondering, no? And
Yeah, yeah. Sure.
and try to make the link, no? But it's really interesting the way that you are using optics to try to explain the vegetation growing, no problem. I really like it. And the last thing I would like to ask again or to point it out is about the dynamics that you observe on your or these locations. I think that well, it's a rich dynamic. Maybe you can find some turbulent or chaotic behavior behind. Have you take a look on that? It's,
Yeah.
from slide 46, I believe.
Yeah, actually, now that I remember, yeah, as you say, especially studying the amplitude equation, there is some turbulent-like behavior in vegetation. Sorry, in the pattern amplitude. And this turbulent-like is a word or a composed word that I have been using since my internship here, because my first observation in vegetation was a turbulent-like state, actually in the north of Chile. Here I have the picture, I think, but it was in Atacama Desert, where we have some state where dislocations was not well defined, because it was a mix between homogeneous and stripe. So yeah, maybe there is the constant dislocation distribution, and maybe there is also this turbulent-like state that can be related via this amplitude equation and via all the analogies. So yeah, that turbulent-like, it's a concept that has been with me since I started this. It was my first motivation in vegetation, and it could be a good way to turn it around into this dislocation distribution.
Yeah, sure. Maybe you can add to just to give it more like a sustain the Lyapunov spectra also with your power density function. But well, it's just a stuff. So thank you so much, Eduardo. I congratulate you. In my opinion, you did an excellent work. So thank you so much, and congratulations again.
Thank you, Mario.
Thank you, Mario. So now it's my turn before I leave the last words and questions for Marcel. First of all, I congratulate you because it's a very impressive work. Your thesis was really clear. Your previous presentation and this presentation are excellent. I think a lot of people, even people without too many understanding about the subject, can actually learn something about it. So congratulations about that. Let me ask you more philosophical questions, I guess.
Yeah.
I already asked some particular ones. See, in general, can you put this, I think it's 19 or 22, I'm not sure. No, yeah, okay, that's, yeah.
This one or
19 maybe.
19? Go back.
Yeah, well, I guess it's all of them, I'll say. Yeah, I was not, yeah, actually 21 maybe is a bit better.
This one is new.
Yeah. Yeah, this is really interesting because essentially I was wondering whether because in essence you're looking for, I like the word, I mean the language of multifractals. So in essence here you're computing the main fractal of the system, but you would expect to have more fractals around. I mean, usually these things are not that simple, right? And you have clearly you have a change of scaling around, I don't know, 10 to the minus 2 or something, something like that. So I was wondering, do you think you can learn something about that? I mean, something new if you study the multifactor behavior these days?
Yeah, of course. I mean, I'm not very familiar with the multifractal topics, but of course, as I mentioned to Mustafa, every tool, it depends on who they use it and how they use it. So it can give some interesting information on the spatial distribution, of course, and it can be also, because some of these tools are better if we can compare it to the experiment. There are some things that, or some tools that we cannot do numerically or that we cannot do experimentally. So maybe that would be a good tool that we can use in every of these three approaches, and also more robust, maybe. So yeah, that would be interesting to check.
And how would you relate this alpha with the Salis distribution, for example?
Yeah. Yeah, no, that is actually one thing that I wanted to do. I tried very rapidly and I didn't get the results that I wanted. That is maybe coupling two of these quenched KPC equations, coupling two to sort of build a stripe, and then checking if the width of these stripes gives this Q distribution. I tried in the very simple way. I simulated one of these quenched KPC equation, and I simulated that they were two like front to front, and I didn't have the Q distribution of Salis. But I would think that it's all related, and maybe we need to couple two of these equations in taking into account what Adrian asked me and what I showed here, that the front and the back are different. And maybe we can recover and maybe do a link between the alpha and the Q. At first glance, I don't know if there is a direct correlation between alpha. I haven't checked that actually. But I would say that it is related, and it will appear if we can correctly rebuild the stripes using these universal equations.
Yeah, because usually when one of my areas of research is space physics. So in space physics, usually to try to reconstruct this Salis distribution of the Q exponentials, usually you take at two different positions. Yeah. And then you construct the distribution of the delta.
I see.
How is the delta X distribution? So that's very useful. Right. But
that is like a little bit what I tried, but I didn't have. Well, I tried very rapidly, as I said, but maybe it can be done like that. Yeah.
And can you go back to 22? That's the last question. Well, not the last question.
There it is.
So here, if you have time, if you have a driver, you can time in the driver, right? Because you assume that this is somehow driven by turbulence, somehow. Moisture or whatever. It's probably a turbulence system, which is usually self-similar. So usually you don't have a scale L or a time T or scale. So do you think would change much? Could you get values below 0.5?
Below 0.5. That is something I haven't think. I would say that, I mean, well, I don't know if it's really turbulent because I've had that question. So maybe there is not very much a self-similarity. So I would think it would change it, but I don't know if it would go below 0.5. Yeah.
Because in essence, you have another scale, right? Which is in turbulence, you also have the inertial range.
Yeah.
You have a place where you cut the inertial range. So that might have.
Yeah, but also the pattern has its own scale.
Sure.
Also.
Sure, but I wonder whether they will be competing at a certain place. And
yeah, that will be interesting to look. Maybe we can do it experimentally by not using patterns. So we remove that scale. We only have a front propagating, and then we can see, And that is something that I can think about how to check them. Yeah.
But in essence, you could have put another Gaussian correlated in time, right? Like a third scale.
I could try it, but maybe, yeah.
Space only, right?
Yeah, of course. Yeah, maybe that would also have an effect, but then again, what is like the physical interpretation of that in vegetation? So,
But you have
what?
time correlation,
Yeah, I mean,
for example, in wind or
yeah, but you mean like wind is turbulent, so it's, yeah, maybe that could be a good, yeah, I could check that, but I don't know if it would change, and how it
so
would change.
you have these eddies, right? That
Yeah.
I mean, if you
Yeah, of
have
course.
a wind hitting some
Yeah.
obstacle, or
Yeah,
something, you
of
have
course.
these eddies moving
Yeah, it's true. I could try with the temporal aspect, and also with the temporal aspect of this dynamic of these parameters, because in vegetation we only study the spatial scalings, but we can also study the temporal scalings and relate that to them. So yeah,
around. And one last question, you were talking about delay feedback.
yeah,
Usually when you have delay feedback, you increase the dimension of your system drastically.
yeah, infinitely, yeah,
Yeah, essentially, right? Well, of course, if you assume that if your time delay is very small,
yeah.
so it has to do with
When
but
approximation.
Clearly, as you increase tau, the time delay your system. So how is this gonna happen here? I saw that you have very complex patterns when you put in time delay.
Yeah, of course. First of all, this allows us to have oscillations, because now we can expand this to at least second order and have these oscillations. But then it leads towards, we think that we may be able to observe spatiotemporal chaos, etc., induced by delay. But for now, we are only trying to taking it perturbedly and having into the more simplest, because this is only starting, the most simplest things that are second order and having these nice oscillations. But then if it goes infinite dimensional, of course, we have some interesting and really useful tools, theoretical tools to, yeah, of course, we have central manifold theorem. We can approximate in the slope variables and reduce the dimensionality in what we want. But yeah, that is something that needs to be addressed.
Because usually a lot of people do numerical stuff with
Yeah.
control, delay feedback, and that, but theoretical is that's a big monster.
Yeah, it's a big monster, but well, theoretically and numerically, it's only the things that have been done more developed, and experimentally, it's more like new.
Sure. Okay, thank you very much. As I said at the beginning, it's very impressive the work you have done. So congratulations, and I know you're going to have a bright future.
Thank you.
So Marcel, all yours.
It's the microphone. Okay. So, okay. First of all, I want to say that I'm very proud for Eduardo. I mean, for me, it's a real integral scientist. So what means that for me is when I propose to him do experiment, he do very well, the theory do very well, the numeric do very well. So every time I propose different problem to Eduardo, every time do result and so on. So for me, it was wonderful to work with him. So I'm very proud for the test of Eduardo, right? So I expect new Eduardo, but it's sometimes difficult to find a new Eduardo. It's not easy, but I'm very happy for our school, our university to have students like you. So I expect we continue with this traditional good student like you. Okay, so you don't, I have only one question that, because one subject you don't speak too much, but I like a lot. This is related to run and tumble. Maybe could you some mention, so maybe the main result of this result, because I like a lot this.
Yeah, of course.
Because he do a very nice and beautiful, very simple experiment that I like a lot.
Yeah. So we go a little bit fast. Firstly, run and tumble is a motion that we observe in the dynamics of bacteria, where they go in a straight line and they suddenly stop and tumble, which means that they reorient and start propagating into another direction. This mostly has been studied using stochastical approaches, Langevin type equations, where the reorientation is mainly the stochastic switch between these two orientation modes, and this leads to nice statistical laws that for short time scales we have a ballistic regime, and for long time scales we have a diffusive regime. But we wanted to take a different approach. We proposed that we can observe this in a deterministic model without the use of stochastic fluctuations. And to do that, we use Turing-Hohenberg equation that has localized states. It would be our bacteria. And we added some spatiotemporal forcing and inertia. Okay. And what we observed with this spatiotemporal forcing, but with others as well, is that the localized states now propagate in a random tumbling manner where these localized states go in a straight line for some time and then they reorient into another direction and exhibit some similar statistical laws that has been reported for bacteria. Now, doing some reductions of this equation using central manifold theorem, we were able to derive an equation for the localized states. This is a Newton type equation, as you see here. It's a potential equation when this potential is related to the spatial forcing, as you see here. It has some inertia, it has some dissipation, and the spatiotemporal forcing. And this is really interesting because this allows us to understand the mechanism of the movement. So we see here that in one dimension, we have this particle on a potential, that the running behavior is due to this inertia in the system. This allows the particle to cross several potential wells. But the tumbling is due to their dissipation that reduces the velocity and the spatiotemporal forcing that causes the reorientation. So now the random tumbling, of course, in this system can be understood deterministically by these simple ingredients, three simple ingredients: inertia, dissipation, and the forcing. And we want to extend this theoretical work with an experimental system. So we build a simple experimental system that has these three simple ingredients. We have a steel ball, has inertia, in a modulated surface. Of course, it has some dissipation due to air, due to friction, etc. And the surface is being shaken, and this gives the spatiotemporal forcing. And what we observed, first of all, this is the experiment. What we observed is that the particles now move. Here I have a video. The particles move. Of course, it's the one-dimensional analog, and they exhibit this similar random tumbling behavior where they travel in a straight line, they stop, they start reorienting, they start traveling into the other way. And interestingly, also it exhibits the similar trajectories and similar statistical laws. Of course, it's not 2 and 1, but this still needs to be tuned. And also this opens a lot of new interesting experiments regarding these particles in modulated surface. We can add now interactions, we can add also with different boundary conditions, etc. So this also, as you said, a really interesting work because it started as theoretically, and we moved on to a simple experiment, but this simple experiment serves us to also understand or explain chaos, because all of these particles, as you see here, start in the similar place, but, sorry, I need to put the video, but as the system starts, because it's chaotic, because it's a three-effective variable system, these particles disperse, so in the same way that a stochastic system like bacteria disperse. But this dispersion, it's related to what has been studied by Maxwell, firstly, that is the molecular chaos. Well, where we understand that at microscopic level, noise or stochastic things are in fact the chaotic aspects of system at the microscopic level. So yeah, this is a really nice thing, and thank you for letting me speak about this. Yeah.
Okay, thank you and congratulations.
Thank you.
Okay.
So now, I don't know how it works on here.
Yeah, press here.
Yeah. So maybe
Yeah.
we're gonna ask you to leave for a second because we have to discuss the